Okay, section 3.5, rational functions. Let's see if that'll focus a little better. That's okay. 3.5, rational functions and their graphs. A rational function has the form p of x divided by q of x, where p of x and q of x are polynomials. This means rational functions are fractions where the numerator and denominator of polynomials. Now remember, we just studied polynomials the last section, and we said to be a polynomial, it was about the exponents and the variables. That your exponents on a polynomial needed to be whole numbers, 0, 1, 2, 3, 4, 5, 6, and that on the polynomial, no variables and radicals or denominators. So when we get to a rational function, it's going to be a fraction, where the numerator and denominator each follow those rules. That in the numerator and in the denominator, the rules will be whole number exponents. That's essentially the rules. And then what that whole number exponent means is no negative or fractional exponents, no variables and radicals, that sort of thing. So rational function is a fraction whose numerator and denominator are both polynomials. Now we've talked a little bit about this domain issue before, but we'll talk about it again. Recall the domain of a rational function is all reals except for any number that causes the denominator to become equal to 0. Because division by 0 is undefined, and so that's why we always have to throw away those places where the denominator will become equal to 0. So if we look at this function, consider the function f of x equals 1 over x. Because x equals 0 will cause the denominator of 1 over x to become 0. The domain is all reals except 0, or the intervals, negative infinity to 0, union 0 to infinity, or in the fancy set builder notation, the set of all x such that x is not equal to 0. On a test, for me, if it's a written test, you're right, I'm going to grade it the traditional way, just get your point across. Find the domain of the rational function. And so it's just all about the denominator. It's going to be all reals except where x minus 4 equals 0, or that becomes all reals except x equals 4. And now if they want interval notation, that's negative infinity to 4, union 4 to infinity. And if they want the fancy set builder notation, the set of all x, such that x is not equal to negative 4. Just for the computer, give the computer whatever they want for an answer. And if you're not sure what the computer wants, you can click through View an Example, and how they answer the problem is how you should answer the problem. Now, View an Example, it's good for that. That gives you a template for what the answer should look like. But really try that when you're working the problems, that you actually work them out on your own, not using any aids other than a calculator, because that's the way you're going to be expected to take the test. You don't get hints on the test. There's not a little View an Example when you're taking a test. So really try very hard to stay away from View an Example and any sort of app, because that's not going to help you come test time. I digress there, but going on doing some more problems here. Find the domain of each of the following. Again, it's all about the denominator. And so it's going to be all reals except where x squared minus 4 equals 0. And then we can quickly solve that dude. And we get plus or minus 2. So all reals except plus or minus 2, which would then be negative infinity to negative 2, negative 2 to 2, 2 to infinity, or that would be the set of all x such that x is not equal to plus or minus 2. Now there is the correct answer. That's the correct one. But someone will do this. Do not do this. That someone will go ahead and factor that, and then they'll cancel those, and they will then say all reals except 2. that they'll just look at just this guy down here, because that's all that's left, and they'll say 2, and that's wrong. And we talked about this before when we did domain of rational functions, that when we're asked about domain, we are asked about the domain as the function is given, not in any modified format. That what you did, or what happened here, when I modified this, I modified the domain. These two things, envision with the x plus 2's gone, x over x minus 2, and this original function here, they are exactly the same except for their domain. Their domains differ. So do not modify the original function when you're talking about domains. It's just not the way you want to do it. And this last one here, all reals except where x squared plus 9 equals 0, which would be x squared equals negative 9. Take the square root of both sides. Don't forget that plus or minus. And right here, we get an imaginary number. The only time we're going to use imaginary numbers is when we're just point blank solving equations. It just says solve the equation, and it's not coming from anything else. The instructions just said solve this equation. Then we might want to use imaginary numbers. But if the equation came from anything else, here it's coming from domain. When we did x-intercepts, they were coming from x-intercepts. When we're doing anything else than just absolutely basic solving equations, we aren't using imaginary numbers. And so this is imaginary, and so this had no real solution. It's no real solution. And so we're going to say the domain is all real numbers. And however you want to put that, there's the interval notation. But like I said again, as far as imaginary numbers, the only time we're going to use that is if the original instructions said solve. If the original instructions said anything else. Here it said find domain. When we were doing x-intercepts, it said find the x-intercepts. If it said zeros, find the zeros. We aren't going to use imaginary numbers then. So here we don't want imaginary, so we get all reals. Okay, so moving on a little bit, that was a little bit of review. Again, we're working to graphing these things. So here I have a very basic rational function, 1 over x. Make a little chart, and here's the graph. And I'll just highlight in the graph itself. There's my graph. And lazy with the graph. There's my graph. It's just nestled in those axes there. Now what I'm interested in is the center here, where one side goes nearly straight down and one side nearly goes straight up. That, in this case, the x, or the y-axis, excuse me, that y-axis is a vertical asymptote. And so we'll put that in red right there. The red is a vertical asymptote. Now it looks like it's crossing there, and that's just me being a little sloppy with my graph. The blue should not be touching the red. It should not be touching the red. But it's down here. In general, a vertical asymptote is a vertical line that guides a graph nearly straight up and or down. The graph never crosses or touches the vertical asymptote. So vertical asymptote, say it again, it's important, is a vertical line that guides the graph nearly straight up and or down, as the case may be. The graph never crosses or touches the vertical asymptote. So like I said, pretty sloppy right there where it looks like it's touching. That's just me being sloppy. Okay, how we're going to find vertical asymptotes. 1, find where the function is undefined. Find where the values equals, where the denominator equals 0. That is insufficient. That only gives you the possibilities for vertical asymptotes. So step 2, substitute the numbers found in step 1 into the numerator. A, if the result from substituting to the numerator is non-zero, then you have found a vertical asymptote x equal number. B, if the result of substituting into the numerator results in 0, you have a hole in the graph x equal number. Note x equal number, the word number refers to the numbers found in step 1. And then important as far as the computer goes, if the problem asks for the equation of the vertical asymptote, the answer must be in the form x equal number. That if the answer happens to be x equal 12 and you just write down 12, it will count, the computer will count it wrong and come to a test that I will be grading, I will count it wrong. A vertical asymptote is a vertical line. Vertical lines are x equal a number. So a little two-step procedure. So we are going to practice this. Okay, in each of the following, find the vertical asymptotes, if any, and the x values corresponding to holes, if any, and the graph of the following rational functions. So again, it's about the denominator. So step 1, I set that denominator equal to 0. And so 2x plus 5 equals 0. 2x equals negative 5, x equals negative 5 halves. That is not sufficient. So step 2, and I go and I look at the numerator. And the numerator in this case happens to be x minus 2. So I take that number that I found, in this case negative 5 halves, and I plug it into the numerator. So negative 5 halves minus 2. I honestly don't care what that number actually is. What I care is what it is not. This is not 0. The fact, that's negative 9 halves? The fact that it's negative 9 halves is not important at all. What's important, that is not 0. And because that is not 0, that tells me that x equals negative 5 halves is a vertical asymptote. So corresponding to a hole. There isn't one on this one. Then the next part is just practicing for the computer. The vertical asymptote is x equals negative 5 halves. Vertical asymptotes are vertical lines, they are x equal. But every once in a while the computer is going to sometimes ask for vertical asymptote, and sometimes they're just going to ask for the coordinate. If they ask for the coordinate, give them just the coordinate. So you got to really read what they are asking for there. And then of course you can check all these by looking at a picture. Graph that dude. Now when we graph these guys, these fractions, you make sure that the entire numerator is in parentheses divided by the entire denominator in parentheses. Entire numerator in parentheses, entire denominator, and then the standard window probably will do it for us. And we are just looking to see that we see a vertical asymptote at negative 5 halves. And if we zoom in a little bit, 5 halves is 2.5, negative 2.5. It certainly looks like there's a vertical asymptote at negative 2.5. And so we know we're absolutely right. These things will check. And that's where we'll end this first video.